All right, well, good morning, everybody, to here in New Mexico on this side of the Mississippi. Good afternoon to everybody that's on the east side of the Mississippi, and then good evening to our guests that are on the other side of the pond. Welcome to the Planetary Science Sample Seminar Series, or as we like to call it. And of course, today, hopefully everybody was good with traveling at LPSC. It was good to see everybody. And we're right back to it now after a little bit of a hiatus. So today we have Carl Hibbitts, who is a planetary scientist at the Johns Hopkins Applied Physics Laboratory. He's an active laboratory program, he has an active laboratory program investigating volatile regolith interactions and the ultraviolet through infrared spectral effects of space weathering on the lunar surface and the surfaces of the Jovian and Saturnian icy satellites. He is the system integration lead of the NASA STMD LSII ISRU focus group, responsible for helping bring industry, academia, government, and nonprofits together for enabling the development of in situ resource utilization technology for a sustained human lunar presence. He has also chaired the recently completed LEAG/XMAG Artemis cold conditioned and volatile sample specific action team report. And then finally, Carl is also a co-I on the Clever and Rassel survey teams, and for the latter is right now leading the development of a cryogenic sample transfer device. And so, Carl,
and he's also an alumni of the University of New Mexico.
Yes, Chip, that is correct. He's also an alumni here at UNM. And so, Carl, thank you so much for taking time out of your day, and we give the floor to you.
That's fantastic. Thanks for the invitation, and Chip, thank you for the invitation as well. It's a real pleasure to be speaking to you all today. As I share screen, I just want to say that I think I met Chip. I've known Chip now for over 30 years. I went to University of New Mexico as an unclassified student, I guess unclassified graduate student at the time, no, undergraduate student, after I got out of the military, after getting a degree in physics from Cornell. And, you know, I'd like to say I have a lot of great stories about Chip, and I could give you a lot of dirty laundry on him, but no, he was a great, I don't actually, he was a great guy to hang with, learned a lot. I worked in the ICPMS facility for a little bit, and that was back when Klaus had just left for Hawaii, I believe, a few years earlier, and Jim Papike had taken over, and Horton Newsom, I knew him very well. He was my senior thesis advisor, and sorry to see him pass. He actually was a lead author, I think, in my first planetary science paper, Impact Crater Lakes on Mars. So it's nice to be talking to everybody now. All right. Fantastic. Right. So this is really going to be a brief and incomplete discussion about the analysis capabilities for, lunar cryogenic samples, transfer, storage, etc. I'm going to start off, though, talking about the science motivation behind it, because everything is really science driven. And this animation gets to that point that the focus really on the South Pole and the return of volatile rich samples from the South Pole. What is needed to return them, but also what do we need to be able to do to analyze them, store them, transfer them effectively. Then after that, I'll talk a little about some of the laboratory capabilities out there and where we need to go. All right, so now we've had the 100,000 foot view. Let's move on to talk a little bit about the volatiles themselves at the South Pole, because that is why we're doing cryogenic sample return analyses, to understand the volatiles, the interaction with the regolith, and the evolution over time, so we can understand origin and things of that nature. And there's really three flavors or types of volatiles, and these are those that are sequestered, cold trapped, at the South Pole, ice being the most notable one, but there's a lot of other materials as well. And these are both endogenous and exogenous materials. As we already know, there's a lot of, there are some volatiles trapped in the minerals themselves, left over from the formation of the moon. And more recently, over the last decade or so, there's been a realization that there is actually OH and potentially H2O formed in the very surface of the regolith grains that's on the illuminated moon through solar wind processes, through the implantation of protons, even though the things are implanted as well. And this is continually very low level. I want to point out that a lot of these materials aren't very good for us. So in the process of returning them to the Earth and analyzing them, to the extent that these materials do exist, and it's not just water ice, we do have to be careful with our handling of them to make sure that the astronauts and the scientists doing analyses are kept safe. But the abundances should be quite low. Still in all, safety first. I already talked about some of this, but it's useful to hit it one more time. in detail, because this is really the essence of why we're doing what we're doing. And this is, I give credit to Bethany Ullman, Caltech, and the Trailblazer mission with coming up with this graphic, which I'm not even sure I modified at all, put some words on top of it. Volcanism, endogenic stuff, we don't have it anymore, but those volatiles almost certainly still exist in some shape, fashion, and abundance and form at the South Pole, sequestered there, and returning the samples from there will allow us to understand how much and what the composition was of that volcanism, coupled with contributions of volatiles from asteroids and comets that can be varied, as well as IDPs, and I mentioned solar wind already. And all these materials are being affected by processes that have occurred and continue to occur, impact processes, thermal migration, temperature-driven migration that can lead to their, actually for solar wind-produced stuff, lead to that cold trapping at the South Pole. You have athermal processes that tend to sublime them, the electron or ion induced desorption, sputtering, as well as UV photolysis and sputtering. But I don't want to forget for that, there is one other source of volatiles that we need now to keep reminding ourselves about, and that is humans. As we land on the surface of the moon, we'll be putting down a whole lot of, tons, literally tons of rocket exhaust that's dominated by water at our, isotopic ratios, as well as maybe hydrazine and things like that for monoprops. Okay. And finally, the spacesuits themselves will be outgassing slightly, and at the abundances we're potentially interested in collecting at, and not just at those abundances, but at these monolayer abundances, this is something we need to take into account. And itself can be interesting science. We can look at the propensity for the materials to absorb the water from the spacesuits or from the rockets, and understand the reactivity of these materials by keeping them pristine or pristine enough. And that is really the challenge. At what temperature, et cetera, do we need to maintain and analyze our samples at, so we can interpret the science that's returned from samples taken from places like this, where it's cold enough in the permanently shadowed regions for the water ice to be stable over geologic times, a billion years. But of course, we're interested only in years at the most, and even minutes and hours when it comes to analyzing these materials. And it's not just water ice, it is also, as I mentioned previously, a whole soup of cometary and volcanic materials, the first insight to which we were able to get from the Cabeus Alcross mission that impacted into the Cabeus crater, and excavated a material that was high enough so that it could be illuminated by sunlight, and spectroscopy measurements were taken and then interpreted, the models fit, and a rough composition was derived from it. That includes things such as H2S, SO2, CO2, ammonia, weird things like mercury, etc., as well as CO, hydrogen, and a lot of water, mainly water. And from ground, apparently there's a sodium exosphere as well, which some of you probably know more about than I do. Some of these are very low abundances, and thus we care about keeping them pristine. Some are at higher abundances. And these abundances, as I mentioned before, are controlled by not only the source and sink, but also, I should say, the sink temperature, yes, and also the evolution that occurs. So this is on the left, a thermal stability map, or I should say the depth at which water ice would be stable over geologic times on the South Pole of the moon. And it shows that sure, PSRs are white, meaning that the water ice is stable on the surface, at least in those parts of the PSRs. But if you go down a few centimeters, several centimeters, then water ice can be stable for long periods of time, not too far down. But clearly, therefore we want to sample all that and sample it carefully. We have to be aware of the fact that these volatiles will have experienced eons of temperature excursions due to potential obliquity variations in the moon itself. That is shown schematically on the graph to the right. Won't spend much time on it. So shows that current period upper graph. The black line is the current distribution of temperatures in the PSR at the South Pole, compared to what it used to be like when the obliquity of the moon was at different angles. And the blue, green, whatever color dot, that's the temperature of the Alcross impact site. All right, and above that is also the temperatures at which these materials will be stable at geologic times. So 1 meter per billion years, which equates to 1 nanometer per year, which is more stable than probably we need for most of our analyses, but in some cases not. For instance, if you're looking at individual adsorb molecules, adsorb layers, so monolayer, one might care about losing a monolayer in a day or two, which is not that far off from that stability point. And then the bottom line is just simply temperature day and night to the South Pole. We could skip over that, and we've talked about this already. The point is that for hypervolatiles that are shown up there, we don't know much about them. And so when we sample the materials, we don't know if it's going to have a lot or a little of them, and we should expect perhaps that the forms would be a lot of adsorb forms that we have to therefore take care of, as well as potentially ices, though those are less likely for the more hypervolatile materials. Again, I talked to this a little bit when I delve into it, just slightly more to set up the stage. And this graph came from a paper that Chip wrote just last year, and it stemmed from the work that he did as part of the League XMAG specific action team that we were part of. And Chip was really the thought leader in understanding the science that can be retained and lost for various volatiles at various temperatures of both collection, transport, curation, and analyses. And it's important to note that on the left-hand side, you have the temperatures for the different materials that they're stable at over geologic times. But again, and I can't repeat this too many times, time scales really matter. And at the time scales of not just curation, but of analyses, we can handle excursions up to warmer temperatures briefly, even if we're concerned of materials desorbing over time and we want to curate them maybe at colder temperatures, right? As an example, if you look in the middle column, the return of ices in vacuum sealed containers for 11 days. How long can they remain stable without significant degradation? And potentially minus 90 C is adequate for returning bulk abundances of volatiles that would otherwise need to be stable at, say, 100 degrees, even colder than that, right? So this is a fantastic start that needs to be looked into more detail when designing these sample transfer and curation facilities for understanding the timescales and what we're trying to keep stable, whether it's very, how pristine we want to keep these materials. It's worth noticing that minus 90, minus 80 is in the realm of achievability with current freezer technologies. And if you want to go colder, you might as well go all the way cold, at least in terms of dunking it in liquid nitrogen. It, as in maybe the container it's in, not the sample itself, and keeping it at liquid nitrogen temperatures. As you see at 77 Kelvin, a lot of materials, they aren't stable over geologic times, but they'll be stable over long times. Now, stepping back and forgetting about ices now, one of the most popular discussion topics over the last decade, it has been the interaction of the surface of regolith with the solar wind. And I'm going to get into the analyses techniques later, and the fact analyzing that has been a driver for some of the techniques that we're going to use for the more volatile materials. And on the left, you see the schematic of a proton schematically coming in, hitting a grain on the surface, idealized when it hits, either considers hydrogen, interact with the bond bridging oxygen, maybe form OH or form clusters of H2. I didn't get too complex like that, right? In reality, you see it's far more complex on the surface of the moon. More processes are happening, at least on the surface of this grain. You have nanophase iron, amorphous rims. You have, as you see later, vesicles, which you all know more about than I do, I am sure. And this is a result of a complex process, almost certainly involving micrometeoroid impacting, which would interact with the surface of the grain, create a superheated plume, really, in which one would have a non-equilibrium chemistry occurring. One can form water directly from that incipient reduced surface that is proton rich, and of course from nanophase iron. At least I believe that's a theory of the formation of the nanophase blebs. Then they get redeposited. Water can get trapped in vesicles in the process, etc. But some of this process some of the water can also be free to migrate around, either through that process or maybe through migration and absorption to migrate around the grains, as shown here, but also more locally still, a little wider, migrate into the surface to cold trap. All right, so we could expect to have water, monolayers of water in the surface of the moon on the illuminated moon as you dig deeper down, depending on how much water migrated down, how recently it's been disrupted through, impact processes. But some of that water will, of course, migrate up, travel around. Some be photolized, some it won't be. Eventually, to migrate to the poles, be sequestered, and go deeper. So, understanding the composition of that water, understand isotopic composition, understanding is all part of understanding its origin, evolution, understanding if there's a global process on the surface of the moon that we think there really is, through this diurnal and latitudinal variation of water on the moon. Now, by water, it could either be OH or H2O. Sometimes it's difficult to tell the difference remotely because the spectral signatures can overlap. And the spectral signatures are shown here on the lower left, where that is infrared wavelengths here, 2.8 to 3.6 microns or so. And where the light is absorbed at that wavelength is being absorbed by the presence of either OH or H2O. Now, in this case, we know that's MAR it's looking at. So at this wavelength, we know it's OH. In an orthocytic material, hyaline material, the OH absorption feature is around 2.95, which is where H2O band generally is. And so it's hard to tell the two apart in just those cases. And we see a diurnal variation over time, as well as a latitudinal variation, meaning it sticks where it's cold. And at the equator where it gets hot, it goes away and goes up and stick where it's cold. And that's actually been to some extent proven empirically through a recent Chinese lander. Wow, it's been 3 years ago already. Chang'e 5, where we are seeing very similar spectra. So we've been oriented. The spectra here, wavelengths here, intensity here. The absorption band of interest right here at 2.9 microns is in this material right here. And I would have thought this to be a hyaline material based off the nature of the spectrum being pretty bland, the blue one, but the band is at 2. Let me hide that. Oh my God. Do you guys still see it? Because I lost it. There we go. I assume everybody can still hear me, right? Yes? Hello?
Yeah, we got you, Carl. You're all good.
Okay, good. All right. Hey, if there's any questions, I'm totally good with questions being asked during the time. I know generally you reserve last 15 minutes, but whatever you all want to do. I don't know how many people are online. All right. But I do enjoy the science. I always want to focus on that because that's a driver. So what the point to this slide is very simply that when the Chang'e 5 lander landed and the exhausts interacted with the surface, it scoured the surface, erased the upper millimeters, centimeters away. We know that, right? The concern is that, because we can see that visually, the concern is that maybe the water from the lander would actually stick and it would be a false signal. False in terms of thinking there was pre-existing water when there really wasn't. But in reality, the opposite happened, which is that it simply was ballistic and it blew the soil away, the regolith away, did not stick. It takes a bit of time. Absorption isn't instantaneous in most cases. So that the regolith here is shown here, D9, which is blue, has no absorption feature, no water at all, right, in it. Now, if only one saw the regolith, one might mistakenly think, well, okay, guess no OH in this landing site. Weird. All right. But in reality, there are rocks. And these rocks don't get blown away. The surfaces remain exposed, maybe gotten more dusty, less dusty, not really sure. And this rock retains a OH band. What this means is that the water is potentially ephemeral. The surface that's exposed has OH in it. As soon as it's buried and protected from the protons, it loses its water. And which means that when we bring this material back to Earth, we don't want to keep it at room temperature. We want to keep it at cryogenic temperature so that the rate of desorption or migration is very slow. Now, it's governed by Arrhenius-like equations, very exponentially dependent with temperature. So simply getting down to minus 90 C is probably good enough. The equation can show when that is based off of given measurements. And work by Georgia Tech and all, which do show that those temperatures, it should be extremely stable. But thermal excursions, up to room temperature the landing sites are warmer, desorbs it when it's not otherwise exposed to rejuvenating protons that can replenish the OH. Right? Now, where does it go? As I mentioned before, it could go to the poles, and this isn't just made up. People have seen evidence for this, not just through the Cabeus impact, but also through remote sensing measurements of the poles by instruments that weren't really designed for it. The M-Cube instrument on Shanjian 1, if I remember correctly, right? Long time ago, as a instrument that goes out to 3.1 microns, barely able to detect 3-micron band, which is why we know there's OH in other parts of the moon. But it certainly covered the 1 to 2.5 micron region, and through careful co-adding and data analyses, there's evidence for either frost or exposed ice in some of these PSRs. We have similar evidence from albedo measurements from Lola and modeling, etc. So maybe there's an active process, maybe there's not. In order to understand that, though, finally we get into the part of the discussion that I advertised I'd be talking more about, is how to actually analyze it and the conditions we want to do the analysis under. During our study, we really came up with 4 different temperature regimes where the science is particularly enabled or lost by keeping or getting to colder temperatures. These are basic ambient. These are somewhat below freezing, well below freezing, and then also really cryogenic liquid nitrogen temperatures. And you can see, based off of analyses of Artemis 3 science goals, that's who funded our work, you can see that a lot of science are lost in ambient conditions, except for regolith only processes. But once you get colder, right? Once you get significantly colder, but still within the realm of current technologies for freezers, at least at the bottom end of it, a lot of the science is kept, not fully. And even in the cryogenic conditions, cryogenics are not all equal. Some are more equal than others. Colder temperatures are more important for preserving colder materials. And same stays true for intermediate. But a lot of science is maintained at these temperatures, right? So how do we conduct the science? And this March Madness bracket that's been modified to show the curation areas and also the techniques. That gives some insight into the techniques that we use, and also, again, what is capable at these various temperatures. So this is just this green definitely recommend is a ad hoc, quick and dirty approach to saying, yeah, at this temperature, one can do a lot of analyses of volatiles in the grain because of the migration is so slow at these temperatures, right? But as soon as one wants to start looking at surface processes, and that's where vibrational spectroscopy, whether it's reflectance or Raman or whatnot, gets into, one cares much more about surface science, and that is particularly, and that depends on which volatiles you're interested in and what you're looking for, right? And especially true for temperature programmed absorption by definition. Once you start its measurements at a temperature colder than the coldest volatile ice of interest, right? So depending on the science, different temperature ranges are of interest. It's important to also point out that, again, not only time, but also pressure is important. And some of the work that we'll want to do will always be at low pressure, like ultra high vacuum, because we don't want to have exchange of gases with the ambient atmosphere at all. So I'm going to talk briefly about the work that I do, and then then we'll talk about some related work and talk about the techniques used. So some of the work that will be used, techniques used to analyze samples that are returned, are being explored in various labs. One of them includes mine. We'll be getting some Bennu samples shortly that we'll be practicing on as well. Now, this lab is not tailored for actually analyses of extraterrestrial samples. It can do them. It's tailored more for the interrogation of terrestrial simulants to make them look like extraterrestrial samples that we then analyze under relevant conditions to understand the observations that we see from space, right? So this setup is ultra-high vacuum, poor ultra-high vacuum, mid 10⁻⁹s. We do a lot of work in the -7 range because we're doing we're now exploring proton implantation to simulate solar wind and magnetospheres at temperatures from 100 Kelvin to 150 Kelvin. And we heat it too, of course, coupled with laser radiation micrometeor simulation with an ability to do concurrently, well, after the irradiation, but altogether spectrally, or one after the other without changing the sample, UV through 8 microns or 7 microns work. So this is the picture. I need to rotate it about 120 degrees to orient it with the diagram here. And the key is that the message, take-home message here is that this is homemade, right? This is tailored. This is not a standard capability. It's been built up over a long time to do very specific measurements. And we're beginning to realize, and we are realizing, that even the sample preparation has to be very carefully done, or we alter even the simulants. Specifically, our ice gets icy if we aren't exceedingly careful with the preparation of them. So we're developing a capability that could be useful for others interested in this kind of work, looking at volatiles under and I'd even say volatiles as well as hydrated materials under cryogenic conditions. So everything is done in a box, of course, but in this case, it is the work is done in liquid nitrogen as well. The sieving, the grinding, liquid nitrogen, everything's maintained in liquid nitrogen. After the samples are sieved, they're put into vials that are then cooled to liquid nitrogen temperature, then put in a -90 degrees freezer. And then in the same box, and we had to do these in 2 stages because we only had 1 box. We had to move the sample prep out and then move the analyses equipment in. We are now getting another box in a week or 2 where we can have 1 dedicated to each, but they'll be attached to each other, so we could go from one to the other seamlessly. We do the spectral analyses of the sample, also maintain that liquid nitrogen temperature. The point, again, is have to keep it cold at all times. That's very challenging. And you have to keep it free of all water at all times, also very challenging. So maintaining the environment is key. This is something I'm sure several of you know as well or better than I do. In this case, we're simply doing reflecting spectroscopy from the visible through 2.5 microns. If one really is interested, I mean, we are interested, but if one really needs to get into the details of the volatiles and especially organic volatiles, one wants to go to longer wavelengths. And this is where using that UHV system that I showed you previously. I'll go backwards. Usually don't like to do this, but I'll show you. That's where using this system is important because it's capable with FTIR to do that, the longer wavelength range. One could create a system like this as a FTIR on it, so you don't have to move to another system. That'd be great. But then one wouldn't be able to irradiate it and otherwise molest the sample to make it look more like space weathered. This is work that's very similar to what being done at Georgia Tech with Christina Buffo down there. Did some really good work. I think her paper is just being submitted or has published. I fortunately don't have a copy of that, but I'm verbally advertising that one anyway for some very good work. You can reach out to her for more on that. This is really not a good example of my work because this is just a really quick put in some wet soil here, about a couple of grams, and froze it after freezing it and irradiate with a laser to break it apart and look at it spectrally. We also do much smaller samples down to 50 milligrams. But anyway, the useful part was that the spectra are somewhat interesting in that this shows you the value. I'm not going to get into the science because there's not enough time. And to look at the broad spectral range. And this is something that analyses, I would argue, will want to be able to do to the extent possible. So you don't have to send the same sample from one institution to another. One will probably want to have as much capability at any individual institution as possible because keeping the sample pristine is very important. On the right, I intentionally put frost on it, right? So that was intentional, but it's still hard to keep from getting frosted. Having a process, a sample transfer mechanism with appropriate capabilities is something that we're working on. Anyway, the point is that, great, these spectral features each tell you something different about the same thing, water, whether it's bulk ice here at 1.5 and 2 microns, ignore that. That's not ice. Or the 3 micron band, which is indicative of small amounts of ice and or water, interior water, to the 6 micron band, which is indicative of water, H2O only, but not necessarily in the crystalline state, though more work needs to be done to really understand that 6 micron band. Okay. And then you have volume scattering peaks and things like that that shift and grow depending on the grain size and abundance. So a lot of information there, and one really wants to do that in one area. Similar to the point that another science that I would say is very, very important. To go back to here, I would call this qualitative. All right, the work I do, although I do it very precisely, it's kind of qualitative because we aren't getting optical constants that can be used to model. Now, we are developing a new facility that will be able to get us optical constant cryogenic conditions, even of irradiated sample. That's going to be wonderful, right? But this work here at Georgia Tech, to mention them again, and other people do it. I believe Ralph Kaiser does in Hawaii, not sure. They have the capability of looking at individual layers or equivalent layers of water and other volatiles, and do what's called temperature programmed desorption, which I mentioned before. And here, pristinity is exceedingly important. One is very interested in the surface nature. In fact, that's what controls these profiles, which are with temperature and then desorption rate. So by desorbing it slowly, as one raises the temperature slowly, one can fit the desorption release, the rate of it, to an Arrhenius-Stahl equation, whether it's 0th order, which means it just goes away, 1st order, some depends on abundance, and I think 2nd order means it's like, oh, it actually do some chemistry, has to convert to something else and then leave. The point is that this is an expression or result of volatile regolith interactions. It depends very much on the surface properties of the regolith. One cannot have the regolith exposed to the atmosphere, or it will be compromised. Chemistry will happen, it will be altered. It will no longer be, in our case, a lunar regolith. There will be a regolith sample formerly known as a lunar regolith, and it will have different desorption characteristics, and that very likely is true. I mean, that is most certainly true of these samples, which were lunar regolith. When we get actual lunar samples back, we should expect much stronger 2nd order effects, much more chemisorption onto those samples, because they will have active bonds in them. They're going to be broken apart, fresh surfaces with very active chemistry ready to happen. And as soon as it happens once, it's once. These are like one-shot return samples when you're interested in understanding the surface reactivity. There'll be pressures that way. So we got to treat those very, very carefully. And those will have different analyses requirements and curation requirements than bulk analyses that I do, or if one wants to do isotopic analyses, right, as well. Okay. Speaking of which, then, even different than that is the analyses of the regolith itself and the volatiles that's put into that regolith, which is it's work that I think is quite mature out there, and it's always improving and getting more capable, and there are machines that are already set up to do this. So the challenge they're going to have is that instead of having individual, unique facilities that are tailor-made, they will each have a machine built by a different company. Each one has a very specific interface, and how do we get those interfaces? How do we work between them? How do we get a sample that works? We can take from one to the other, maintaining that ultra-vacuum if needed to make these measurements, right? We need to address this, and we simply need to address these. But there's a lot of capability that exists there that we'll be using and already being used. And most of the examples will be from Purdue, because the clever team, the Razzle team, Michelle Thompson is a co-I on it. And as you all know, she does incredible work. So she was gracious enough to give me some slides. But I'll be speaking to them. So that's the only drawback to it, is that I'll be speaking to them instead of the spectroscopy that I understand. The point of this is that I am floored by the amount of work that goes into preparing the samples for analyses. And here's an example preparing for, as you see, the transmission electron microscopy here, using fibs. You can see that it's quite difficult. And this is done actually under cryogenic conditions. So the capabilities now exist to enable that. We can leave it open to discussion on how important it is for this to be done at cryogenic temperatures, given that the hydrogen, the helium, the water they're looking for is in the grain, and it may not be affected by warmer temperatures. That is certainly up for discussion. At what level of pressure and temperature is really needed. But there's no question that this is some intense work, and transferring samples from one laboratory to another and maintaining the pristinity of them is going to be exceedingly challenging, so that these samples are not altered too much. Okay, and here's an example. You read a cell Apollo 17 Highland sample there, looking at the formation of water and of course amorphous glass and hydrogen in them. I think that maybe some of that's going to be work to be done. Here are some EELS spectra of the hydrogen, helium, and water vesicles that was derived from her work. You guys have probably seen this at LPSC presentations and in papers of her, as well as Alexander Kling and and Zoe Wilbur down in Arizona does very similar work as well. Now, this is, for those of us less familiar with this work, maybe you'll find this as fascinating as I do at the description that took straight from this paper, what's necessary for doing this kind of work. Those are done at room temperature. But to my point, looking at helium in a sample requires a whole lot of work. In this case, didn't have to be done under vacuum. Was it under vacuum? Didn't have to be done under cryogenic temperatures because the thermal evolution and the migration of helium was slow enough that one can still do decent sample analyses, and arguably similar for looking for water, whether it's Alexander or Kate or whoever doing the work here, right? Good. All right, and so finally, as I mentioned before, the question being asked here is more related to and this is going to be very interesting, is how these samples differ in the PSRs versus on the illuminated surface of the moon. On the illuminated moon, this is what is occurring, right, through the combination of solar wind implantation, micrometeor bombardment. How is that different in the PSRs, where the solar wind implantation is indirect, and there'll be more surface water available and micrometeors impacting, and then you form this rind on top of that? How is that space weathering going to look compared to typical lunar style space weathering? And to what extent do we need to keep those samples colder than currently returned samples because of the nature of that difference? And I'd argue, we probably need to keep that. I don't know how cold that is. We need to work at that to understand it, and to understand how much that water is going to migrate through those samples, et cetera. How to preserve those samples? Do the vesicles form in the same way, et cetera, et cetera? Now all that is out there. So what I want to finish up the last 5 or 10 minutes after after having talked about the science is what little we do have in terms of, and we talked about the capabilities as well, which I said I would talk to. I'm very interested in talking to the technology used in order for transfer of these samples back and forth, because without adequate sample transfer, then all the analyses and all the collections, all that's a moot point. The sample will have been irrevocably altered, even though, yes, a short duration exposure doesn't necessarily destroy a sample, but one doesn't necessarily know that either. Okay, so these are some results that you can read for yourself. And on the sake of time, I don't want to really spend that much time on that, but instead want to talk about a little bit more measurements. I almost forgot about this one. Yeah, this is, shouldn't have admitted that on the telecon, but Anders Maibaum, interesting story with him. I actually knew him when he was a postdoc in Hawaii and I was a grad student. And now he's running a facility in Switzerland doing cryo nanosims and cryo SEM. Other institutions are as well, but I happen to be reading on this paper and thought it was quite interesting. Again, this is an example of a I would say, I presume, a rather homemade approach. Very, very nice looking approach. Multiple cooling apparatuses, vacuum cryo transfer, which gets to the point of vacuum cryo transfer from one area to another, or when you put the sample in, et cetera. But how do you do vacuum cryo transfer from one system to another complete system? Now, in this case, as I understand, it looks like nanosims, it has a whole whole slew of preparation requirements as well. Now, I do not know how widespread this will be used. This appears to be quite popular in the biology area because they're looking at the, in this case, I think nitrogen isotope uptake and ratios in organisms. One may have a very similar question for adsorbed species and et cetera on the surface of grains that are returned from the surface of the moon to understand the origin of those volatiles, based off of isotopic analyses. So this may be quite a applicable parallel. That is why I have it there, even though this is focused on biology. So a lot of complexities there. And you can see they show the importance of it. Here on top is regular SCM and nanosims under vacuum and room temperature. Basically, it desiccates, and it really affects the distribution and concentration of the nitrogen isotopes compared to preserving the structure down on the bottom. I can imagine we'd want a very similar capability for understanding the surfaces of grains, because that is where active processes occur. And there are only a few capabilities out there for that. And what he uses is like EM, this great capabilities for what he needs, but for what we're doing, which is not bulk ice, we'd be more interested in the small abundances. A pressure of this is inadequate. We need to be at ultra high vacuums, like 10 to minus 9, 10 to minus 10, to keep even a monolayer to form, because the standard number to keep in mind is that at 1 times 10 to the minus 6 torrs, you effectively get 1 monolayer of interaction of volatiles per second. And so even at 10 to the minus 9 torrs, that's 1 monolayer in 1,000 seconds. So it's not even an hour. So, time is both your friend and your enemy. There is one COTS sample transfer suitcase that we found, and we were considering its purchase. And in the end, decided probably not to do that because of the limitations this imposes on us. It only works under UHV conditions, and its sample ability to manipulate the sample is not as versatile as we'd want. And so we're going to focus more on that. But this is a very interesting approach. I'm going to finish up in the next couple of minutes, looking at the time, that it keeps the sample 10 to minus 9, 10 to minus 10 torrs, cryogenic, and you can move it in and out and transfer it between institutions. It has a liquid nitrogen dewar on top of it, or you could put a refrigerator on top of it, a cryostat, like a helium cryostat or something, if you need to transfer it, as long as you have power. That is also a question that we need to deal with. So this moves, I think, small amounts of things. I'm not going to say what small is, but small amounts, right? End effectors are set up for standardized interfaces, so that can be advantageous when dealing with standardized equipment that such as shown just previously, right? Okay. And so let us do the takeaways. It's now 40 minutes, just what we're shooting for, right? So there's significant scientific, a lot of reasons for doing this, right? A lot of reasons, especially from the polls in terms of doing this being cryogenic sample analyses. We have a lot of capabilities that are being adapted to the science needs for the moon. Researchers are already doing this. They aren't waiting. I think the sample transfer and curation needs to catch up to the researchers. And that's especially transfer between institutions, but also just within one facility itself. This is where a lot of the work needs to be. We saw a few examples. We need to work on them more, and we need to work on them in collaboration with, I'd say, the vendors themselves that build these things, as well as individual researchers and institutions that are developing the capabilities themselves, so that we have a system approach to this and not a stovepiped approach of I do my work and you do your work, and I don't want to compete. I don't want to work with you because we're competing for money. Yeah, we are. We truly are. But hopefully we can still find ways to work together for a common approach to the analyses. All right. So I'll just end on that note, and I can take some questions.
Thank you so much there, Carl. We'll go ahead and
Sure.
open the floor up to questions. Anybody online or anybody here in person, if you have questions online, go ahead, raise your hand. You can also put it into the chat, and then for us here in person, go ahead and just raise your hand. I'll go with Carl AG first.
Hi, this is very, great talk, very interesting. Do you envisage this being a robotic sampler on the moon or a human sampler on the moon? I mean, it seems you were saying like time is your enemy here. And obviously the moon is a better target for that than Mars or an asteroid. So how do you get it into your system? How do you pick it up off the moon?
Yeah. All right. So that's a fantastic question. You know, when we go to the moon, it's going to be a combination of human and robots, right? We're going to have humans and robots working together as teams of some nature, and there was some kind of partnership at some level. That's a whole different question, right? But I'm certain that initially it's going to be mainly humans because the robots aren't yet developed to the capability needed for sampling. So initially it will be humans sampling it. But clearly, Carl, if you're implying it, and it'd be viable to have robots do it because robots can go into PSR safely. They can access samples without contaminating them. They can take all this contextual information that's required to understand the science from the analyses when you turn it back. Is absolutely, I think, spot on if you're referring to that. I would also go a step further and say that back on Earth, maybe this is where we develop the robots that would then be used on the moon. Because I would argue that in these, in the sample preparation area, it's very difficult to work in a glove box, right? It would be easier if we could have robotic arms. And by the way, we're purchasing one to do just this, not to mess with the sample, but to take spectral measurements. That's very simple for a robot to do. Just move the arm to different positions repeatedly. Perfect for a robot, really hard for a human. But there's no reason, a lot of reasons, but there are no permanent reasons why we can't have teleoperation locally for the working with samples in glove box. Yeah. And that could be even teleoperations on the moon too, if one wants to go that way.
Thank you, Carl. We'll go ahead and do a question online. Mike, you have your hand raised?
Yeah, hey, can you guys hear?
Yes.
We got you.
To continue on that the chart show the science available.
I can't hear you, Mike.
Oh. Can you hear me now?
You're cutting out.
Can you hear me now?
A little bit.
Oh. How about now? Let me speak a little.
Sure.
Okay. I was wondering if you guys have thought about, let's say in the situation that, say, -8, the sample is proper, and maybe because of mixing chemistry.
Mike, if you can you put your question in the chat, please? Thank you.
Sure.
Yeah, you couldn't hear that either. Okay.
Yeah. And then in the meantime, Mike, while you write down your question, Chip, you have a question?
Yeah, Carl, you know, we really didn't do this in our study, but it's something that needs to be done. And this is kind of a follow-up to Carl's question. You know, obviously surface activities on the moon to get these samples really will evolve from just, you know, preliminary samples under room or crew cabin conditions to very, very cold cryogenic conditions in terms of collecting samples and storing them before you return them for curation on the moon. Has there been a study yet that really balances the cost risk with the science return for the investments that one has to make in returning these samples?
I'm not aware of any. Are you?
No, that's why
No, I'm not aware of any at all. I would argue though that we don't know enough though to do a cost risk study like that because we don't. It's a question of discovery. It's a truly bringing samples back from the moon from PSR is going to be truly discovery. So we don't know what we're losing. My personal thought on this is that we should approach this like a comet surface sample return mission. You know, either you intentionally, you know, collect the samples and keep them cold somehow, like a comet nucleus, or you devolatilize it, keep the volatiles separate because it's too hard, or you just collect the surface material and let it warm up and you get what you get. I see it at that level, at least initially for it. But to your point, those missions are very expensive. And so we have to keep that in mind. And we'll have to take what we can get to some extent.
Well, thank you, Chip. Okay, so thank you, Mike, by the way, for putting your question in the chat. So Mike is asking, in the situation where returned ices are partially melted and we receive a soup, in quotation marks, do you have thoughts on if the sample temperature should be decreased or maintained at the soup temperature?
Well, I'd say we really screwed up if we brought back a soup, right? I mean, that's bad. Clearly, you want to cool it off to stop any further chemistry from happening. At least to me, it's clear. I'm not a chemist, but that's what I'd want to do. Now, if one's worried about a soup happening, then once you do what I previously mentioned, intentionally devolatilize it under vacuum and capture those samples in another matrix, such as zeolites or something that will preserve them without chemistry happening, and keep that at a cold enough temperature, whatever that is. And if that can't get cold at all, then fine. Keep it separate from minerals, right? So you aren't actually altering the regolith. There's no reason why one should allow the volatiles to heat up and alter the regolith you're collecting, because then you lose all your science. I'd prefer to intentionally degas it before returning it than risk a soup, in all honesty. That's my thought. Chip and others may have different thoughts, though.
Thank you, Mike, for putting your question in the chat. We still have a few more minutes for questions if anybody has any further ones. Steve, go ahead.
Yes, a couple questions about the cryogenic fib. One is, where is this instrument located? Was it Ohio State or Purdue? And doesn't the fibbing process heat up the sample at all?
Yeah, good question about those two. I think it's Ohio State, but I'm not sure. Have to ask Michelle Thompson on that one. So she knows. Sorry about that one. And I wondered if it heated it up too. And I also wondered what's the ramifications of it heating up. So those are very good questions. And unfortunately, I only thought of that question when I was preparing for the talk, so I didn't get a chance to ask her.
Well, thank you.
There we go. Alexander answered the cryofib. Very good.
And Hope has also answered that there are cryofibs in many facilities, and with care, sample heating is minimal. So thank you, Alexander and Hope.
What is minimal, if I may ask a question on my own talk? Good, yeah. Minimal to me may not be minimal to Mike.
That's what you're looking at. It's like being classified.
Well, in the meantime, Brianna, do you have a question?
Yes, I do. Hi, this is Brianna Henderson from JPL.
Oh.
Hi, Carl.
Hey.
Good talk. So I was wondering about, you mentioned temperature and time are important for curation and also pressure. So I was wondering if there's any tricks that you can play with the samples to actually pressurize them and prevent some of the volatile loss instead. I'm wondering if anybody looked into things like that.
Hey, you read my mind. I think that's a great idea. I don't know how effective it'd be and how to do it exactly, but yes, I think that's just something to explore. Because you said, now I'm not sure, and you as a chemist knows better than I, but it will still be unstable to some extent. You may have lost in atmosphere at high pressure. You aren't talking really high pressure, are you? Or are you just talking ambient pressure?
I'm not sure. I think it should be something people look into.
I agree with that very, very much on that one. And that
Can you guys hear me better now?
Oh yeah, I can hear you, Mike.
Oh, excellent. Yeah, no, to follow up on your pressurized sample, yes, we absolutely are thinking about this, right? And for example, one scenario would be we pressurize the sample chambers with 1 bar of argon.
Figure out and hopefully come up with a path of working together for the best way to figuring it out.
I think it might be a bit difficult to do that because even though you pressurize with 1 bar of argon, you will still the water will still vaporize until the water saturation of vapor pressure is satisfied. Yeah. So it might be very difficult, almost impossible, I think, at least, for example, using argon to pressurize the sample chambers.
Okay, thank you.
Well, thank you, Brianna and Mike. And then to follow up with what Hope had said in terms of minimal, the clarification is polymeric samples do fine, but not sure about smaller molecules. And then any other questions, comments, or concerns, testimonies?
Yeah, I've got another question.
Okay, go ahead, Chip.
Yeah, Carl, as you know, there were a number of samples. This is tied to your discussion about potential human contamination of the volatile reservoirs on the moon. And as you know, there were a number of Apollo samples collected underneath the LIM vehicles to really look closely at the interaction between the regolith and the exhaust. And I know a lot of measurements were made, you know, in the 70s and maybe early 80s. Have there been more recent measurements made on these samples with some of these contamination issues in mind?
I think, again, here, Chip, you know better than I if those measurements were made. But my concern about astronauts contaminating the sample is really limited to those in PSRs, in their PSRs, where it's cold enough for them to do it. Now, yeah, under shadow conditions, sure, samples cool off already, but there already wasn't probably any volatiles on them other than solar wind that's implanted in them. No adsorbed phases, no SO2 from flying around old volcanic ices or anything like that. Now, my concern mainly is that astronauts can put a thin veneer on a sample and adsorb species that would be present in PSRs but not present on luminary terrain, right? That those adsorbed species could be replaced, affected, altered through those kind of contaminations. So I think PSRs are a unique environment for worrying about even small levels of volatile contamination compared to the illuminated moon at lower latitudes. That's
Well,
my thought, at least.
Thank you, Chip. We have time pretty much for one last question. So Kate, go ahead.
Hey, yeah, Carl, I was curious if you guys, kind of what came out of discussions for like one big facility. One of the difficulties you talked about a lot in your talk was transferring the materials, you know, even within a specific facility, but especially between institutions. So going forward, are we looking at it being better to have a concentrated facility with a lot of these equipment and instruments, or everybody's kind of on their own getting what's commercial or what they can buy for themselves? And
that's a really loaded but very good question,
well,
right? I mean, that better means like, well, from a Procore perspective, I want it at my place, right? You know, but from a science perspective, maybe NASA should do everything. They have amazing facilities, you know, or not. Maybe NASA, you know, in all honesty, won't be able to improve quickly enough due to bureaucratic process. Who knows? You can have a lot of things you want to optimize on, but I think we do need to go down the path of optimizing for them and deciding the path forward, but also keeping in mind it depends on the science that we're doing, right? Depending on the science that you're trying to do, really defines just what kind of care you have to take with the sample and during transfer and during analyses. So that's just another way of saying it depends. It's a complex question. And the good thing is that we're asking it now, well before we get the samples, and hopefully we can prepare. But my druthers would be to have multiple institutions and share the wealth to the extent possible and solve the challenge of transferring between institutions. I think that'd be the most elegant solution. That'd also be most inclusive for the community in a good way that enables science to go forward. But I also recognize that having a single entity, a JSC, whatever, right, was amazing for Apollo. So, you know, I'll leave it up to you. I mean, I'll be part of the discussion, but you know, and Chip can speak, and then the younger generation, Alexander, I see him there. He needs to weigh in too as well, and everybody else. I don't happen to see your name on the screen right now.
Thank you, Kate, for the question. And unfortunately, we are out of time. So if anyone has any, you know, further questions or you know, further comments or anything, please reach out to Carl. And certainly the discussion will continue on, you know, as we move forward.
I just want to finish up, if I may, real quick. Like, we do need to figure out this conversation and maybe form a community of practice, whatever you want to call it, to work together on this. And I think the CASA survey group and Razzle and Clever, whatnot, the survey is a great way to really get this going.
Yeah, absolutely. And beautifully said. Thank you, Carl. And again, thank you, Carl, so much for the talk today. One last time. Before we sign off, next week we will have Thomas Orlando and Alicia Vera from Georgia Tech joining us again, same bat time, same bat place. So we look forward to seeing you guys here next week. In the meantime, everyone have a wonderful rest of your weekend, or wonderful rest of your week, and enjoy your weekend. And we will see you all next week. Thank you.
Thank you.